Hello, everybody. Welcome to today's lecture. So, today we're going to get started on Chapter 7. We're actually going to do all of Chapter 7 today because I really just want to go um, ahead and give like an overview of the chapter rather than getting into the specifics. This chapter is about something called the central limit theorem, and it's hard to go into details without using calculus at all, and the book does a good job avoiding it. But what ends up happening is you really just have to talk conceptually about it rather than diving into the specifics. And when the book does dive into specifics, it's always done in a calculator or with Excel. In the name itself, the central limit theorem, limits are the key concept that you learn in calculus. So it's baked right into the name. It's very hard to avoid it. So we're just going to talk more generally about it so that we're kind of aware of it, of what it is and how it's used, because we're not necessarily going to need it for any calculations, but we will. It does come up in showing where certain ideas come from. Okay. So that's kind of why we want to know about it. So the central limit theorem, let's write it out. The central limit theorem, it's probably the most important theorem in probability. Okay. The central limit theorem, or the CLT for short. Okay, we abbreviate it because we use it a lot. As the book says, it's one of the most powerful and useful ideas in all of statistics. Okay, it's really more of a probability thing, but that it kind of bleeds into statistics, of course, as we're seeing. There's two kind of forms of the theorem, and they both have to do with means. So let's look at the two ways it is stated. Okay. So the first way we could think about this is if we collect samples of size n, okay, so our sample size is n from a population, hang on. If we collect samples of size n where n is large, okay, putting this in quotes because it's a little ambiguous, right? Calculate each sample's mean and create a histogram, which is essentially a bar graph. Then the histogram will look similar to the bell curve. Okay. So this kind of sounds weird, right? And that's just because we're avoiding calculus so much. But that's what we got to do. So if we collect samples of size n, where n is large, so n being large is ambiguous, right? And it's ambiguous because it's going to be different in every context. But if you make it, the idea is if you make it large enough, eventually when you make this histogram, it'll look similar to the bell curve. So the idea is if it doesn't look similar to the bell curve, Then if you went back to n and increased it, eventually it will look similar to the bell curve. Okay. So what this would look like is we would have something okay, not drawn perfectly. Okay, but something like this. Hey, when we eventually drew the histogram, it would have the same shape as the bell curve. Remember the bell curve looking like this, right? Um, so and that the bars here are the samples means. Okay. We're creating a bar graph of the means. So like this would be the first samples mean, maybe this would be the second, this would be the third. It doesn't have to be in order though. Like maybe this is the first samples mean, this is the second, this is the third, this is the fourth, etc. Okay. If we were to rearrange them, we would eventually get it to look like the bell curve. Okay. So that's one way to think about what the central limit theorem says. The second way, if we collect samples of size n, again, that are large enough, calculate the sum. Sorry, it's in this paragraph, so it's hard for me to keep track of where it is. Calculate the sum of each sample and create a histogram. The resulting histogram will resemble the bell curve again. Okay, so this first definition is about calculating each sample's means. This one is about calculating the sum of each sample. Okay, so that's the only difference between them. So we would have the same picture if instead of each one of them, each one of the bars representing one of the samples means, it represents the sum of the samples. Okay. So let's state this with math symbols a little bit better. Okay. So with our symbols, let x be a random variable. Let x be a random variable. Remember, this just means that it's a variable that has some kind of probability associated with it. Okay. With any distribution. Okay. So we don't know what the distribution of x is. Let mu subscript x. So remember, mu is the population mean. We're going to use a subscript of x for the population. Sorry, I should just say the mean of x. Okay. And then we're going to let sigma with the subscript of x be the standard deviation of x. Okay. So we're just using mu and sigma still. The subscript x is just because sometimes we have more than one in one problem. Like maybe we're talking about two different random variables, x and y. So we'll use mu subscript x to be the mean of x and mu subscript y to be the mean of y. Okay. So that's all the subscript means here. So what the central limit theorem says is that if you draw random samples of size n, then as n increases, so as n gets large, whoops, the random variable x bar, remember what x bar is, this is the, remember we use little x bar to mean the sample mean. So big X bar is the sum of all of the sample means. So we're kind of taking the first and second thing we had here with the sum of the samples and the mean of the samples and combining them into one statement. So X bar, which consists of sample means, tends to be normally distributed, and more specifically, X bar is normally distributed with mean mu x, so the same mean, and standard deviation sigma x divided by the square root of n. Okay, so it has the same mean as x, but the standard deviation is a little different. You take the original standard deviation and you divide it by the square root of n. Okay. So there's some important ideas here that it's kind of glossing over, namely this x bar. X bar, it's maybe not immediately obvious that if x is a random variable, x bar, which is the sum of the sample means, is also a random variable, but it is. Okay, let me elaborate a little bit more on what x bar is, because the book just, like I said, it kind of just glosses over this. It might have, maybe it was in another chapter that we skipped, but I don't think so. X bar is equal to x1 plus x2 plus xn divided by n. Okay, so it's just like the sample mean formula. You take your first random variable, you add your second random variable, you keep doing this for all n random variables, and then you divide by however many there are, which is n in this case. Okay. So why does it end up having the same mean? Well, we can figure this out actually just using some of the definitions we had. If we think about what the mean of this one is, x bar, it's going to be Here, let me write it out. The mean of x bar is the mean of x1 plus the mean of x2 plus the mean of xn divided by n. Okay. So when we're finding the mean of x bar, all we have to do is take the mean of everything in the formula. More commonly, we'd write this as the expected value, which we introduced, I think, in chapter 4, but we can write it as the mean just as well. The mean is what's known as a linear function, which means that we can write it just like this. Now, each x1 is just essentially one of, it's just like a offshoot of this x. So they all have the same mean as this x. Okay. So that means this is mu x plus mu x plus mu x because they all have mean mu x. Okay, and there's n of these. Okay, so let's say this is n times. But if there's n of them, that means this is the same thing as n times mu x, right? Just by the definition of multiplication. And then our n's cancel, and we get mu x. Okay. So I'm just showing you where this comes from. How do we know that the mean of x bar is mu x? It's okay if you don't feel comfortable replicating this. I just want to show you where it comes from. The standard deviation is a little bit more complicated, and it gets into some other properties of variance that we never talked about, so I'm not going to go through that one. But essentially, it's the same idea, except it doesn't work out as nicely. You have to do something extra with the n there. Okay. So this x bar, which is so you take the sum of all the random variables and then take divide by n, so you get the sample mean of the random variables themselves. It ends up being normally distributed. This is a very powerful statement because notice that x could have any distribution. Okay, it could have the binomial distribution that we talked about. It could have whatever. Eventually, we'll be able to turn it into a normal distribution. I mean, this is so powerful because this means that literally any data we have, we could view it in terms of the normal distribution. Meaning, the normal distribution is very important, and that's why we study that one so intensely. Okay. So that's pretty much all of. Here, let me write on the side here. Note the z-score then of x bar is z equals x bar minus mu x over sigma x over root n. This isn't anything new, right? We always define the z-score, we subtract the mean and divide by the standard deviation, okay? But we are often trying to find the z-score, so it's worth stating here. Normally it wouldn't look this ugly where you have like a fraction in your denominator, so you have a fraction underneath another fraction, because you'd have actual numbers here, right? So there's only a couple more things in 7.1 I think are worth mentioning. All right, so sigma x bar. So with our notation, this would mean the standard deviation of x bar, which is sigma x over root n, right? Because we said the standard deviation of it is this. Is called the standard error of the mean. Okay. It's important because this is the first time we've really talked about error. When we take a sample and we're using it to make predictions about the population, it's not going to be 100% accurate. There's going to be some kind of error involved. So it's important for us to know that error. You might think of this like, well, we'll get into that later, but so this is called the standard error of the mean. So we'll see this a little bit more later, how this is used. But just keep in mind that there is a way for us to calculate numerically what the error of something is. Okay. So we'll be able to predict exactly how accurate our predictions are. Um, 7.2, I'm gonna kind of skip over. It pretty much goes through the same thing, except for it does it with only sums. So with this one, we're talking about the mean of the sums. In 7.2, it does the same thing, except for it does it only with the sum. So it goes with it writes, sigma x for x1 through xn, and it goes through the central limit theorem for this. It's all the same because our x bar is that same thing. It's just divided by n. So if we just multiply this by n, then it would be the same thing. And then so our mean ends up just being n times mu x. This one ends up being a little bit different because you can't just multiply in for the standard deviation because the formula for standard deviation is more complicated than that. But it's close to the same thing. It essentially just has the square root of n on top instead of on the bottom. Okay. So let me just write out sigma x is equal to this. This is also a lot of times called Sn for sum instead of sigma x, but the book is using sigma x. I'll use Sn though. It's the same thing, except now it's going to be n mu x and square root of n sigma x. Okay. So it just has a different mean and a different standard deviation. Okay. You can see where the n mu x comes from because in the way we derived it, the n's canceled out. But if this n isn't on the bottom, they're not going to cancel out. So it's just going to be n mu x. The standard deviation, like I said, it's a little more complicated, so we won't get into that. But this is the entirety of what is said in 7.2. Nothing more to it. Let's go to 7.3. Okay. So one thing that's important to note. Okay, this is the first note on 7.3. If you are finding the probability of one value more precisely of an individual value. Do not use the CLT. Okay. You would just use whatever the distribution of the random variable is. Okay. So the idea is if we're finding the probability that x is say like bigger than 0, right, where x is the same as before, we said x could be any distribution, we don't use CLT. Okay. However, if we're finding the probability that x bar is greater than 0, or the probability that Sn, or sigma n if you prefer, is greater than 0, here we would use CLT. Okay. So if we're told that x has some distribution with mean mu and x and standard deviation sigma, and we're told that x bar is the mean of all of these x's, then we can use the CLT for this, because when I say use the CLT, we just use the fact that x bar is a normal distribution with this stuff. So we would go ahead and we would find the z-score, and that would be it. We'd do 0 minus whatever the mean is minus this number. Let me just do an example here. How about that? Let's let the mu of x be 10, sigma x be 2, n equal 1000. Okay, remember n has to be large, but it's ambiguous what that means, so we'll just say it's 1000. Or maybe let's just say it's 100. The book notes that it should be at least 30. So I guess make sure it's at least 30. If we want to find the probability that x bar is bigger than 0, okay, or maybe let's just use like 5 or something like that. Okay. So we know from the formula up there, x bar is normally distributed with mu 10 because it has the same mean. And the standard deviation is 2 divided by the square root of 100. Okay. So it's the standard deviation divided by the square root of n. Okay. Which, if we want to simplify this, the square root of 100 is 10. So this is 2 over 10. Or if you want to even simplify it even more, it's 1/5. And if you want even more, this is 0.2. That'll make it easier to put in the calculator. So we're using the central limit theorem to say, okay, we know x bar is normally distributed with mean 10, standard deviation 0.2. Okay. So then we would find the z-score. Okay. The z-score of x bar would be z, and we're looking for it at 5, right? So we'd have 5 minus the mean, which is 10, divided by was it 0.2? Yeah. So we would find 5 minus 10 is negative 5, divided by 0.2 is 25. Which is going to be way too big to even be on a table, honestly. So maybe yeah, I mean there's no way that's going to be on a table. The probability of this is going to be basically 0 because this number is so big. So maybe I mean I just picked bad numbers. I guess if we go ahead and we want to make this probably at least like let's say 20. And this would be 20. And this one would just be 2 because we do 20 divided by 10. Okay. So we'll just make this 2. And now this would be negative 2.5. So that one should be easier to find on a table. Let's go ahead and pull that table. Okay, so I got the table pulled up here. This is just that same Wikipedia page. We want to find the area to the right of negative 2.5 because that's where it would be greater than, right? If you think about like this curve, right? If we're saying x is greater than negative 2.5, it's going to be the area to the right. So this table, the only table with negatives on it is the one that gives you the area to the left. So we'll need to do 1 minus that. So here's negative 2.5, which is 0.00621. So the answer is going to be 1 minus 0.00621. Okay. Which is going to be like basically 99% again, but at least it's the first value was just so big that it wasn't even on the table. Okay, so this is going to be 0.99379. So the probability x bar is bigger than 5 would be it's about 99%, 99.379%. Okay. All right, so the last thing I want to mention here is that it does talk about the law of large numbers, which is something similar. The law of large numbers says that if you take samples of larger and larger size from any population, then the mean x bar of the sample tends to get closer and closer to mu. Okay. So, law of large numbers. The gist of it is that as n increases, x bar gets closer to mu. Whoops. Remember, x bar is the sample mean, mu is the population mean. We're trying to use x bar to predict what mu is. So the bigger our sample size, the closer these two numbers are going to be. In other words, we should make our sample size as large as possible because it'll make our predictions better. Okay, that's all the law of large numbers says, and the central limit theorem is just kind of an example of this. It's basically saying the same idea, and you can use the you can basically use one to show the other. Is the idea is why it's being brought up here. Okay. But we don't really need to go over it too much. The important thing we want to take away from this chapter is that we know the formula of x bar is the normal distribution, and we just want to use it as a formula for a problem like this. Okay. Same with the sums. So that's going to wrap up the probability portion of this book. Okay. So that was chapters 3 through 7, essentially. So starting next time, we're going to get started on like the heart of statistics, the heart of inferential statistics. So we did descriptive statistics in chapter 2, where we're just describing the data. So now we're going to look at how do we run tests, how do we make predictions. We're going to start with confidence intervals. So we're going to talk about how do we calculate a confidence interval, what is a confidence interval, why is it important. And then after that, we're going to talk about hypothesis testing, which is very important. It's like, if you have a hypothesis, how do we test it? How do we know when to accept or reject the hypothesis? What is a p-value, which you might have heard of? How do we know if something is statistically significant? Okay, so we're going to start to get into the heart of these questions. We need this probability to really do that stuff. Like p-values, for example, are just probability values. So with the central limit theorem, especially, if the details don't make complete sense, it's okay. It's because we're glossing over a lot because we don't have calculus. We just really want to know the key ideas of it, some basic facts about it, like this formula, and then we're going to apply that in order to come up with some new ideas involving the confidence intervals and stuff like that. So starting next time, we'll start really getting into the heart of inferential statistics. So thank you for watching this video today, and I will see you for the next one.